Today I want to take a quick look at the DIY BMS and the EP-Ever Tracer A that I set up to solar charge this 7S20P lithium ion pack. I've been watching it closely over the last 10 days or so, and there's a few things that I'd like to amend. The first thing I want to do is look at the charging parameters which I've set inside the EP-Ever Tracer A. And most importantly, the float charging voltage here and the boost recon charge volt as well. I really want to make sure that the float charge doesn't happen, because that's meant to be quite a bad thing for lithium ion cells. I'm really grateful to Superbrain AK, who commented on my last video that perhaps they were a little bit low, and let me try and explain why. Well, let's imagine I'm having a good solar day here in the shed, and my batteries have got up to the 28.7 volts. Well, after 120 minutes, the solar panels are going to be completely disconnected from the battery bank until the voltage drops to this 26.5 volt level. So if I'm using power during the day, well, the battery bank is going to have to supply the current until it drops to that 26.5 volts. The solar panels won't be delivering any current to my load, and that seems very wasteful. So I think I'm going to change that now to about 28 volts, or what's that, 4 volts per cell, and I'll allow a boost recon charge voltage at, I don't know, 27.5 volts, something like that. Let's give those parameters a go for the next few weeks. Next, I want to talk about the DIY BMS controller software, and I have to say Colin Hickey has done some excellent work here on top of Stuart Pittaway's original code. Not only has he added the ability to cancel an average balance, he's also added a button here for resetting the controller, but I have to admit I've never had to use that button. My controller is running very reliably. The biggest thing that people were crying out for has been improved as well. In the configure section, if I scroll down, you can see that Colin has implemented an auto balance section here, and you can turn that on or off, and you can tell it at what voltage you want the balancing to start. So I've set that to 4.1 volts. I don't see the point of wasting any energy in my cells until the point where they're going above where I would like them to. So if the average cell voltage goes above 4.1 volt, then this should kick in and automatically start balancing. I've also set a maximum allowed cell voltage, and even with auto balance off, this particular setting will kick in. So the maximum allowed cell voltage is 4.15 volts, and then the module should go into bypass mode and bring that voltage down. So that's all working really well. Colin has also made an improvement to the module section, and there is a bypass status here. So from a distance, using this web GUI, you can see whether any of the modules are in bypass mode. That will be indicated with a number 1. So I have to say, in the last couple of weeks, this software has come on leaps and bounds, and I'm very personally grateful to Colin Hickey for all his work. There are a couple of really minor hardware changes that I would like to make. The Wemos D1 Mini is actually powered here by USB, and that's actually powered from my 12 volt lead acid battery bank, and I'd prefer that the Wemos was powered by the lithium ion battery bank. So at some point I intend to put a buck converter in that will allow for up to 30 volts on its input and will happily regulate 3.3 volts on its output. So the Wemos will actually be powered by the same bank that it is monitoring. And it's probably worth taking this opportunity to point out that the Wemos and this connector here and the connection to the next module has a completely independent power supply to the rest of the module, which is powered by the lithium ion pack it's connected to. And that's all down to the ADU-M1250 ARZ I2C isolation chip here at the top of the module, which essentially isolates the whole of this module away from this I2C bus and the Wemos. And the only other slight modification I'm going to make, I'm thinking about removing this resistor here and putting in another value. Now we're looking at the schematic that Stuart has kindly made for the DIY BMS module, and the resistor in question is this one down here, R12, and Stuart has put it in here. It's a current limiting resistor for this LED, and he's set it at 2K2, 2200 ohms. Well, let's think about that for a moment. This ATtiny is powered by a 3.3 volt rail, and a green LED typically has a voltage drop of 3 volts or thereabouts. So 2K2 is awfully high, and that's probably the reason why I've never seen my green LED turn on. And in fact, if we look at the schematic that I drew originally, it's this one down here, which originally was a 510 ohm resistor, which again might still be a little bit high, but for some reason that got swapped out for a 2K2 resistor. But I think probably something in the tens of ohms rather than in the hundreds or thousands is probably more suitable. So at some point in the future, I'll certainly be swapping those out. One of the things I have noticed over the last couple of weeks of using the DIY BMS is that cell 3 seems to charge the quickest and discharge the quickest as well. So I guess the cells in here could have a slightly lower average capacity than the rest of the packs, but actually I think it's more likely that either a dodgy solder joint or a bit of damage has happened. And if we look here, yes, I think that fuse there has broken, so I need to repair that. And not only that, there's another one there as well. That one's broken as well. It's kind of touching, but not soldered. So I need to fix those two, and then hopefully this pack will have the same capacity again as all the others. And there we have cell 3 back into the battery bank, and hopefully now it will track the other cells a little bit more closely when it's being charged and discharged. And that brings me nicely onto a little frequently asked question about the DIY BMS. And that perfectly valid question is, are you sure that 22 ohms was the right decision to make for your bypass resistors? Is 150 milliamps of bypass current going to be enough to keep your pack in balance? And I have to say, for the last 10 days, yes, it has been. These packs have been beautifully in balance. Apart from the issue I had with cell 3, these are tracking each other really well. And yes, the bypass resistors are coming on occasionally, but they're keeping this whole battery bank perfectly in check with just that 150 milliamps. And of course the argument is that that's less than a couple of watts, and I've got 200 watts of solar coming into the tracer. But remember, the tracer is already ramping down the solar when these are getting anywhere near their high voltage point, that 4.1 volts per cell. So actually there's probably only a few watts coming in when the bypass resistors come on, and it's so infrequent that actually it all seems to be working well. But obviously I'll keep monitoring it, and never say never, perhaps a 10 ohm resistor might appear one day. The other regular question I get is, will it do 3S, will it do 4S, etc, etc, and the answer is yes. It will do as little as 3 in series, because remember it's doing an average balance, so it needs at least 3 modules for one of them to be above or below the average, so 3S is minimum. And I think Stuart has designed this, and in fact I think he's using it with a 14S system. So this will work anywhere between 3 cells in series and 14 cells in series, as long as of course you've got a module for each pack. The most frequent question I've been asked, especially in the earlier videos, was, will it auto balance? Well, Stuart Pittaway's code doesn't auto balance. You have to press the button to initiate a balance, but Colin Hickey has come to the rescue, hasn't he? And his software will do an auto balance, and you can set and forget. And the last two questions are very similar. Can you buy these modules pre-completed? Well, I'm afraid no, you can't. You need to buy the components and put them together yourself. And the last question is, Adam, can you make me some? And I'm really sorry, but no, I can't. I don't have enough time to get all my projects done, let alone doing them for other people. So sorry, you'll need to find somebody else. And that brings us nicely onto the very last question, which is, how much does the DIY BMS cost? Well, your mileage may vary, but this is exactly what it's cost me to put together. The biggest costs are the PCB, the Adam 1250 ARZ and the Reg 710 regulator, and then closely followed by the ATtiny 85s. The rest of the components are pretty cheap, to be honest. I mean, they're only resistors, capacitors and a couple of LEDs. It doesn't matter how many modules you've got, of course, you only need one WeMOS, and in fact that's almost the simplest part of the project, and that only costs a few pounds. So all in all, each module cost me £8.31, which in today's currency is about $8.31 and €8 as well, isn't it? So all 7 cost me £58.18, and the controller cost me £3.45. So in reality, for less than, I don't know, $70, that sort of price, I've built this whole DIY BMS. And I've probably not used the cheapest suppliers here. There's a lot of RS components in here, and Farnell, both local to me and a fair bit more expensive than the Chinese eBay sellers or AliExpress. Now, I will place a link to this spreadsheet in the description below so you can look at this a bit more clearly, and all these links here will take you through to the supplier at least, if not the product directly. So yeah, go ahead and click and see if you can find them cheaper. If you've been following this series of videos, I do hope you found this little frequently asked question and update video useful and entertaining. If you did, give me a thumbs up, subscribe down below, comment if you can, and I will see you next time. Thanks for watching.